And this is Math 348, Lecture 2 on the homework problems that are the beginning problems on linear programming. There are 5 problems from section 3.1, numbers 2 to 6. And I'm going to go through some of them. It's useful to have graph paper, but it's not necessary. 3.12 asks us to draw 3 regions in the plane. So in the first, we want to find the points x1 plus 3x2 less than or equal to 6. And we have our non-negativity conditions. We're only looking for x1 greater than or equal to 0 and x2 greater than or equal to 0. So there are several ways to do this. You could write this in the form of a line if you like. You could say that this is 3x2 less than or equal to minus x1 plus 6, or x2 less than or equal to minus a third x1 plus 2. And this is the equation of a line with y-intercept 2 and slope minus a third. So this is 0, 2, 4, 6, and this is 2. This line has y-intercept 2 and slope minus a third. This is equal to 0 when x1 equals 6. So this is the solution to the problem. We just draw that region. You could also do this in a slightly different way. If you have x1 plus 3x2 less than or equal to 6, when x1 is 0, 3x2 is less than or equal to 6 means x2 is at most 2. So this is the y-intercept, the point x1, x2 equal to 6 when x1 is 0. And when x2 is 0, you get x1 less than or equal to 6. So x1 equals 6 is the x-intercept. So you could just draw the straight line from 2 down to 6. You get the same result. B, we have the region 4x1 plus 3x2 less than or equal to 12. And again, the same non-negativity conditions. What can we say about this? Well, if x1 is 0, 3x2 equals 12 when x2 equals 4. So this is the y-intercept. Right? When x1 is 0, x2 can be anything from 0 to 4. 4 is the y-intercept. When x2 is 0, you get 4x1 less than or equal to 12, x1 less than or equal to 3. The x-intercept is 3. And the non-negative points in the plane that satisfy this inequality are this triangle. For C, we have the inequalities 4x1 plus x2 less than or equal to 8. And again, when x1 is 0, x2 goes up to 8. When x2 is 0, x1, 4x1 less than or equal to 8, x1 is at most 2. Right? So x1 equals 0 means x2 goes between 0 and 8. When x2 is 0, that implies that for x1 is at most 8, or x1 is at most 2. So this is the region. So this is the solution to problem 2. Sorry, A, B, and C. Now, part D, combine these constraints into a single graph to show the feasible region for the entire set of functional constraints. So let's do that. The highest value on the y-axis, on the x2 axis, is 8. The largest value on the x1 axis is 6. So let's take a look and see what we have. So for part A, we had the triangle going from 2 to 6. For part B, we went from 4 to 3. For part C, we went from 8 down to 2. And what is the region that's common to all 3 of these triangles? What's the intersection of the triangles? Or what is the region in the plane that satisfies all 3 constraints? And it's this region right here. That's the solution. Let's look at the next problem, 3.13. Consider the following objective function, z equals 2x1 plus 3x2. Draw the graph for the values 6, 12, and 18. So suppose we have z equals 6. That means we're looking at the line 2x1 plus 3x2 equals 6. So for this line, when x1 is 0, x2 is 2. When x2 is 0, x1 is 3. This is the line for z equals 6. Z equals 12. We want to graph the line 2x1 plus 3x2 equals 12. When x1 is 0, x2 is 4. When x2 is 0, x1 is 6. So we have that line. When z is 18, we're graphing the line 2x1 plus 3x2 equals 18. Again, when x1 is 0, x2 is 6. When x2 is 0, x1 is 9. So the graph of the line is that. This is part A. These are the objective functions for z equal 6, z equal 12, and z equal 18. Find the slope-intercept form for each of these equations. Compare the slopes and compare the intercepts on the x2 axis. So we can make a little table. So when z equals 6, we have the line 2x1 plus 3x2 equals 6. So 3x2 is minus 2x1 plus 6, or x2 is minus 2/3 x1 plus 2. That's the slope-intercept form of the line. And the slope is minus 2/3. And the x2 intercept is 2. This is our table. What about when z is 12? When z is 12, we have 2x1 plus 3x2 equals 12. So 3x2 is minus 2x1 plus 12. Divide by 3, x2 is minus 2/3 x1 plus 4. So x2 equals minus 2/3 x1 plus 4. The slope is still minus 2/3, and the x2 intercept now is 4. And finally, when z is equal to 18, 2x1 plus 3x2 equals 18. So 3x2 is minus 2x1 plus 18. Divide by 3, x2 is minus 2/3 x1 plus 6. So we see that for different values of the objective function z, we get a set of lines that are parallel, and what varies is the x2 intercept. As z increases, the x2 intercept increases. It's all in this table. That's number 3. Section 3.1, problem 4. We have the line 20x1 plus 40x2 equals 400. To find the slope-intercept form, 40x2 is minus 20x1 plus 400. Divide by 40, you get x2 is minus a half x1 plus 10. So the slope is minus a half, and the y-intercept is 10. And to graph the line, see, 0, 2, 4, 6, 8, 10. The line is y-intercept 10 and slope -0.5. So if you go over 2, you go down 1. If you go over 5, sorry, you go over 20. See if I have enough room here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's the equation of the line, and that's the graph. So this would be, for example, the point 10.5. This is 0, 10. This is 20, 0. Maybe what I'll do is go back and label my lines. I had 4 lines. These were my 4 lines. This is the line x2 equals 10. This is the line 3x1 plus x2 equals 44. This is the line 2x1 plus 5x2 equals 60. This is the line x1 plus x2 equals 18. So this point right here is the intersection of this line and this line. What are the coordinates of that point? Well, we have to solve 2 linear equations and 2 unknowns. What are the equations? 3x1 plus x2 equals 18. X1 equals 44. And x1 plus x2 equals 18. What's the solution? Well, if we subtract the second equation from the first, we get 2x1 equals 26. So x1 equals 13. And if x1 is 13, x2 equals 5. So the coordinates of this point are 13, 5. And on this point, the objective function, 2x1 plus x2, has the value 2 times 13 plus 5 is 26 plus 5, or 31. So that's the answer to the problem. You maximize the objective function 2x1 plus x2 subject to the 4 constraints that we had exactly at the point 13, 5 that satisfies all of our conditions. And you get 31 as the maximum value. That's the answer. So this is really the important problem, this is the technique you have to learn. There's one more homework problem, 33.1-6, which I won't do at this time because I shouldn't have all the fun. But I will go over it, and if anyone asks me at the in a problem session, or if someone wants me to do it, I'll do it. But for now, this is our first homework.